Hello and welcome to this video about matrix proofs. In this video we'll prove this theorem, that a square matrix is invertible if and only if its row equivalent to the identity matrix. This seems to be extremely obvious and therefore difficult to prove. So we'll solve it in the reverse direction first because it's easier. We'll define matrix A to be a square matrix. Then we'll assume that it's row equivalent to the identity, and we'll have to show that it's invertible because of this. And we'll write this down more mathematically here. So we know from the definition of row equivalence that there's a sequence of row operation matrices that multiply on the left of A to give us the identity matrix. We can call a function to do this called the Gaussian elimination matrix or gem of A. So E is a left inverse of A because it multiplies on the left of A to give us the identity. Now we're required to show that E is a right inverse too, so as to show that E is an inverse of A, and therefore that A is invertible with inverse E. And that's enough to prove the first part of this theorem. So we'll do a bit of manipulation to show this. We'll multiply E on the right of A, and we can put this matrix inverse pair in front, because E is invertible, being the product of row operation matrices. And we can use associativity to swap the brackets around. And because E is a left inverse of A, this product in the brackets will become the identity matrix. We can then eliminate the identity, being its main property. And so finally we get the identity, showing that E is also a right inverse of A, so E is an inverse of A, and so A is invertible. So we've proven the first part of this proof. Now to prove this theorem in the forwards direction, we'll let A be a square matrix, such that it's row equivalent to the identity matrix. I've written this mathematically as well. So we'll prove this by contradiction, because that's how it's done in a textbook. I tried to think of a proof done differently that was more intuitive, but I couldn't. But if this is presented right, it could be fairly intuitive. So we'll assume that A isn't row equivalent to the identity matrix and try to find a contradiction to show that it can't happen. So matrix A must be row equivalent to another matrix B that isn't the identity matrix, and matrix B must be in reduced row echelon form. We can write it out mathematically like this. B is equal to the reduced row echelon form of A. So B must have at least one row of zeros because it's in reduced row echelon form and isn't the identity matrix. And here's an example of what B could look like. It's in reduced row echelon form and it's forced to have a row of zeros because not all of the columns could become pivot columns. And here one of the columns is a free variables column. So there exists a matrix E that when multiplied on the left of A produces B. And E is a product of row operation matrices because A can be transformed into B using row operations. This is what E looks like. It's the product of a sequence of row operation matrices. It looks like there are m of them here. M can be any finite integer greater than 0. So I'll just scroll the screen up to make some more room. And E is invertible and so contains no row of zeros. This is what we're going to use to form a contradiction. We're going to continue on with the proof to show that E must have a row of zeros. And that'll be our contradiction. We'll start with E and multiply it by this matrix inverse pair. We've stated that A is invertible, and so we can do this. Then we can swap the brackets using associativity. And we know that EA is equal to B, because that's how we defined E. So we know that B contains a row of zeros, because it's in reduced row echelon form, and isn't the identity matrix. So E must have a row of zeros too. We'll use this example to observe how E must have a row of zeros. We'll multiply the example of B that we had before by the inverse of A that we can set to be this. And multiplying them together gives us a row of zeros at the bottom. I'll just circle the row and column used in this multiplication, and the 0 in the product matrix that is the result of the multiplication of this row and column. I'll just scroll the screen up to make more room and to write more stuff. And this is a contradiction, because E can't both have a row of zeros and not have a row of zeros at the same time. Remember when I mentioned this earlier in the proof? So we get this contradiction when we set A to not be row equivalent to the identity matrix. Therefore, A must be row equivalent to this matrix. I'll just make a mention of the fact that the identity matrix is the only square matrix in reduced row echelon form that doesn't have any rows of zeros. So that's it. We've proven this theorem in both directions. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Please write anything helpful in the comments if you can think of anything helpful to write. Feel free to share this video, and thanks a lot for watching.